Lesson 30, Inferential Statistics. Inferential statistics refers to a collection of statistical methods in which random sample results are used to draw an inference, make a statement, or reach a conclusion about an entire population. In general, there are two basic types of inferential statistics methods: confidence interval estimation and hypothesis testing procedures. Confidence interval estimation is used when the issue under investigation involves learning the value of an unknown population parameter. That is, we have no idea what the value of the population parameter is ahead of time, so we can estimate it using confidence interval techniques. Hypothesis testing procedures are used when the issue under investigation involves assessing the validity of an assumed value of a particular population parameter. In this case, we do have an idea what the value of the population parameter is ahead of time. And with all ideas, it's either a good idea or a bad idea. So we use our sample data to test the idea in a hypothesis testing procedure. For instance, a student in the nursing program wanted to know the average starting salary of registered nurses. Well, since the student does not know the average starting salary of registered nurses, she can take a random sample of registered nurses' starting salaries and use a confidence interval to estimate the value. For instance, a counselor told a student in the nursing program that the average starting salary of registered nurses is $50,000 per year. In this case, a random sample of registered nurses' starting salaries can be used in a hypothesis testing procedure to test the validity of the counselor's stated average starting salary of registered nurses. The only way to really know with certainty the value of a population parameter is to conduct a census by collecting data from each and every member of the entire population. It is only when 100% of the data, that is, a census, is actually known that the value of a particular population parameter can be determined with 100% accuracy. Realistically speaking, in most circumstances, conducting a census is either impractical or impossible to achieve. As a result, the actual data collected only comes from part of the population, that is, a sample. Since sample results are not based on data collected from 100% of the population parameter cannot be determined with 100% accuracy. Nonetheless, when unbiased, representative random samples are collected from the population, the results obtained in the sample, that is, the statistics, are used to infer what the results in the population, that is, the parameters, might actually be. In confidence interval estimation, a random sample is collected from the population, and the resulting sample statistics are used to determine the lower limit L and upper limit U of an interval that accurately estimates the actual value of the unknown population parameter, 1 minus alpha times 100% of the time. So to illustrate this idea of a confidence interval estimate, we'll focus on two aspects: the confidence and the interval. First, the interval. A confidence interval is a range of values from some lower limit L to some upper limit U, such that the actual value of the population parameter is estimated to fall somewhere within it. Now for the confidence is referring to the likelihood that this population parameter will be contained within the interval. That is, the population parameter is estimated to be between L and U with 1 minus alpha times 100% confidence, where the notation 1 minus alpha times 100% represents what we call the confidence level. And the confidence level is the probability that the confidence interval accurately estimates the population parameter. So in order to have a great deal of confidence in the estimate, we need to set our confidence level very high. Now, in statistics, the customary value used for alpha, which is called the level of significance, is 0.05. Thus, the customary confidence level used in statistics is 1 minus the 0.05, or 95%. Thus, we can construct confidence intervals that can accurately estimate the value of the population parameter 95% of the time. Even though the value of a population parameter is usually unknown, the actual value is fixed. The exact value could be determined if a census is conducted. On the other hand, since random sample results are used to calculate the confidence interval, the resulting lower limit L and upper limit U produce varying results determined by chance due to random sampling. So to illustrate this, imagine we've collected a random sample and constructed the confidence interval. Now it's the actual data values in the confidence intervals which we use to produce the lower limit L and upper limit U to form the confidence interval. So let's say just by chance we happen to get a few lower data values in the sample. Thus, the resulting confidence interval will estimate lower values. Or let's say just by chance we happen to get a few larger data values. The resulting confidence interval in that sample will estimate a little larger values. On the other hand, we could collect sample data that contains both smaller data values and larger data values. Thus, the resulting confidence interval will produce a much wider range of data values to reflect that diversity in the sample. But if we happen to collect data that doesn't contain any small data values or any large data values, just mostly data values in the middle, the confidence interval estimate will be much more concentrated in the data values in the middle. So just due to chance alone and random sampling, we get different confidence interval estimates because the different data values in the random sample are themselves different. So keep in mind when it comes to confidence interval estimates, the confidence interval themselves is random and takes on varying results just due to chance and random sampling. But what each confidence interval is trying to do is estimate the actual value of the population parameter. And this population parameter value, although unknown, is fixed or constant. It's the target that each of these confidence intervals are trying to hit. So when we say that a confidence interval is accurate 1 minus alpha times 100% of the time, we mean that each time we construct one of our confidence intervals, it has this 1 minus alpha times 100% probability of hitting its target. That is, having the actual population parameter be contained within the interval. Thus, 95% of confidence intervals constructed with the customary level of confidence accurately estimate the value of the population parameter. As seen here, most all of these confidence intervals contain the actual population parameter. On the other hand, only 5% of confidence intervals constructed with the customary level of confidence do not accurately estimate the value of the population parameter. And as we see here, we actually had one confidence interval not contain the actual value of the population parameter. In hypothesis testing procedures, a random sample is collected from the population. If the resulting sample statistics are consistent with the assumed value of the population parameter, the validity of the assumed or hypothesized value is confirmed. Alternatively, if the resulting sample statistics contradict the assumed value of the population parameter, the assumed value is considered to be invalid. To illustrate this, in hypothesis testing procedures, the value of the population parameter is assumed to take on a certain value. Then a sample is collected and the corresponding sample statistic is calculated. If the sample statistic is consistent with the value of the hypothesized population parameter, then we conclude that this population parameter value is valid. But if the resulting sample statistic differs from the hypothesized population parameter, then this sort of gives evidence that maybe the hypothesized population parameter is not valid. But you must be careful when making this sort of conclusion because, for instance, if the particular population parameter in the hypothesis is the mean, mu, and the resulting corresponding sample statistic is the sample mean, x bar, we know that the result of the central limit theorem tells us that the distribution of the sample mean x bar follows a normal distribution. And just due to chance alone, if the actual population parameter mean, mu, is true, there is a 50% chance that the resulting sample mean, x bar, will be less than that value. And by chance, there's a 50% chance that the actual sample statistic will be larger than the sample mean. So this is something that can just happen due to chance alone. So just because the resulting sample statistic differs somewhat from the population parameter, we don't necessarily want to conclude that that hypothesized value is invalid. Now in hypothesis testing, what we do is we want that sample evidence to really extremely contradict the hypothesized value. So if the resulting sample statistic is extremely different from the hypothesized population parameter, then we say that we have enough evidence to really contradict it, thus leading us to a conclusion that the hypothesized population value is invalid. In hypothesis testing, the probability that the sample statistic is at least as extreme as the resulting sample value is calculated under the assumption that the population parameter equals the hypothesized value. This probability is referred to as the p-value. So it's this probability, the p-value, that is calculated that determines this result of being as extreme as the sample result just due to chance alone is how we'll reach our decision. When the resulting p-value is 0.05 or less, it would be considered unusual to obtain these sample results by chance alone. Therefore, the more likely explanation of these sample results is that the assumed value of the population parameter is invalid. Thus, when the resulting sample statistic is considered to be an unusual outcome, we reject this hypothesized value of the population parameter in favor of an alternative explanation which is much more consistent with the sample results, thus having a more likely explanation. To summarize, there are two basic types of inferential statistics methods: confidence interval estimation and hypothesis testing procedures. In upcoming lessons, we'll be learning how to construct 4 different types of confidence interval estimates, 2 of which involve the population mean mu, which is an average based off of measurement data. Also, we'll be learning how to estimate proportions, which are percentages based off of count data. For both the mean and the proportion, we'll be learning how to construct confidence interval estimates for just one population mean, mu, and we'll be learning how to construct confidence interval estimates for one population proportion, p. In upcoming lessons, we'll also be learning how to estimate the difference between 2 population means, mu1 minus mu2, and we'll be learning how to estimate the difference between 2 population proportions, p1 minus p2. In upcoming lessons, we'll also be learning how to conduct 4 different types of hypothesis test procedures, 2 of which involve the population mean mu, which is an average based off of measurement data, and 2 involve tests involving proportions, or p, which are percentages based off of count data. Now, for both the mean and the proportion, we'll be learning how to conduct hypothesis test procedures involving just one population mean, mu, and tests involving just one population proportion, p. We'll also cover lessons that allow us to make comparisons between 2 population means, mu1 and mu2, and comparisons involving 2 population proportions, p1 and p2. So, regardless of which inferential statistic method we apply, that is, whether it be confidence interval estimation or hypothesis testing procedures, it's important not to lose sight of the main idea behind inferential statistics. Inferential statistics uses random sample results to reach a conclusion about an entire population.